Thank you, everyone, and thank you for making it all the way up to the 5th floor. Now, obviously, the first session after lunch, hopefully you'll have been digesting for just under an hour now, so brain should be full of glucose and super efficient. And I am going to delve a little bit into human efficiency just to set things in context. So I've been coding since 1984, and I think there are definitely some of you in this room who have been coding that long as well. And back then, BBC Micro, I had 16K of RAM to deal with and very little else, and you had to be immensely creative with the resources you had. And what I've seen, and what has irked me over the past couple of decades, or 3 decades, is people getting lazier and lazier in how they code, and particularly with AI. So for the next 35, 40 minutes, I'm going to go through a lot of the high-level techniques that I use and that I expect my teams to use to make really efficient systems for production. Now, some of you may know some of these, you may know all of them to some extent, you may know none of them. But if you're already running a high-performance computing laboratory, you might not get that much out of this. This is very much a, here are all the things you should be doing. And things that I've found that most people, particularly those I interview in the AI space, know very little about. So let's take a look at our brains. So the last time someone cut a human brain open, which was about 5 years ago, they took, I think it was 10 male brains, and they revised our estimate of the number of neurons we've got down to 86 billion. And if you take the general calorific input for a human in a day, it works out that your brain is using about 20 watts, which isn't a lot at all. Now, your brain's lots and lots of systems with multiple pathways, and just your visual cortex, which has 13 billion neurons, is using about 3 watts. Everything you're seeing, you're reading, you're interpreting is powered off 3 watts. Very, very efficient. And if you do the very simple calculation down to watts per neurons, it's in the region of 10 to the minus 11 watts, which is hardly anything. So these aren't just integrate and fire systems, they're not simple transistors. We have multiple specialized neurons, which is going to become important later when we look at specializations of chips. But there are lots and lots of connections. Lots of connections, and this is what makes us so complex and dynamic and enables us to do immense amount of things at great efficiency. So let's look at computers. So the piece of kit that I use on a day-to-day basis, which is possibly one of the better laptops for deep learning development because it's one of the lighter ones at only 2.5 kilos. It's got a 1050 in it, 4 gig of RAM. It can run most models pretty well. It's quite slow. 130 watt power supply. And if you look at the watts per CUDA core and watts per transistor, it doesn't matter what device you use. As they scale up, those are pretty current. We're not getting any efficiencies, we're just getting more power. And even if you look at Google's tensor processing units, which they're a little bit more closed doors about, I think if I recall correctly, they're about half the size of one of the Haskell CPUs, so about 2.5 billion transistors. And they're an order of magnitude better, but still a lot further out. So neurons are about 1 billion times more efficient than a single CUDA core. So we are starting from a system that's far away from where we are biologically. And if we're going to get the most out of these systems, we need to really sweat them, and we need to ensure that we understand that we're starting from this inefficient position and make the most of everything. So why are we even in this position? Like I said, 30 years ago, we were very creative. We did machine code. We used every single bit we could in the computers. And as the years went by, we've abstracted away from that. Nobody codes their own printer drivers or operating systems anymore. It's a complete waste of time. They're out there, they work, other people maintain them. We have got higher level languages. When I did my PhD, I did it all in C. And it was an absolute nightmare. I could probably recreate those 4 years worth of work in Python in maybe a month now, which is absolutely heartbreaking. But at the time, it was the best that we could do. We're also getting growing resources, and we don't notice how bad things have become because, every 6 months we get new GPUs. We get, CPUs have slowed down a little bit, but the i9's out now. It's more powerful. We've got the new 2080 GPUs coming out. We've got more RAM. We've got bigger machines. We're just adding more and more power onto everything. So we get our new computers and we go, great, everything runs faster. And then 6 months later, we're complaining about how slow it is. And every time we increase our hardware, we're increasing our energy requirements and decreasing efficiency. And if you go back to the keynote this morning, compute requires energy and space and time. And our time might be going down, but we're increasing space up to a point by adding bigger and more cards. And we're increasing energy. And if you look at the wattage for some of those big servers, they take 8 power inputs to power these things. And yes, there is a little bit of redundancy in that, but there is a lot of power that these things chew up. And if you are not using it to its full capacity, you're wasting energy and you're wasting the use of a very, very expensive machine. So I think last time I checked, the DGX1's about 150 grand. So if you can't use the latest and greatest, because not everyone has an infinite checkbook to buy hardware and use cloud compute, you need to be a little bit more creative. So what is efficient? A couple of weeks ago, I was at another conference, and there's a speaker from Qualcomm, Tucker Cohen, who actually said this really interesting statement, that soon algorithms will be measured by intelligence per watt, which I really like, because that supports my thinking, and that is the way that we're going. So how can we get to the point where we get the maximum intelligence, the maximum accuracy for the minimum energy? Now, what you may find, depending on your problem, is that speed may be more important than accuracy in some cases. So I'm going to use the two together as efficiency, because you can, if you're more efficient in what you're doing, you'll have a faster, more accurate system. So start from the point that every flop is sacred. Look after the pennies, the pounds will take care of themselves. And there's been an awful lot recently about speed of training. And this is one of the articles from the Register from over the summer. And yes, you can train a system in 4 minutes, but you need 1,000 GPUs and you'll only get about 50% accuracy. That's not useful for anybody. It's not efficient. And if you look at the speed of training on a single GPU, you get far more energy efficiency and more accuracy than they got. So one of the things you need to think about is where you're making your compromises, but start from the point of view of efficiency. And the basics. The most fundamental thing you can do, and I can't enforce this enough, is learn to code well. Whatever language you're coding in, whether it's C, C++, Python, if you can't code well in that language, you're always going to have a problem. This is a huge problem in our industry particularly, because one of the wondrous things we have is we've attracted people from a lot of other fields, which bring in some wonderful diverse ideas, but they've never been formally taught how to code, and they have no interest unless you push them into learning how to code well. They code to get a job done, and then it's out of the way. One of the guys that works for me refuses to identify himself as a developer. He says he's a statistician, even though what he does on a day-to-day basis is coding. He just hates it so much. Part of that is understanding the boundaries of the languages you use and the frameworks. And we'll go into this a little bit more in a minute, but if you don't know the scope of the frameworks you're using or how they do it, you're basically guessing at the best way to do something, which isn't great. Your code flow is something else that you need to look at. If you don't know how your machine physically takes the code that you've written and runs it, then you won't know how best to optimize it. This is something you can pick up through profiling, but understanding that when you're interpreting something, what is going on, where is the code moving about in memory, where are things being cached, and where are things being output, that's really important. And while you don't need to know all of the really deep mathematics that comes with machine learning and AI, you do need basic computational linear algebra. This is really important for optimization. If you don't have this, then you're going to make problems. So every time you import a third-party library, you're giving away control to somebody else. And quite often people think, okay, that's fine, someone else has coded this and they've sat in a room and they've thought about the best way of doing things. And that's not necessarily true. They've sat in a room and they've thought about doing things that fit the timelines they've got and that work for the problem they're looking at there and then. It's not necessarily your problem. One of my biggest bugbears, the number of times I've had to debug AI code that's broken, and I've had data scientists swear to me blind that nothing has changed. It's because they've pasted something working from Stack Overflow and it's trashed a local variable. And they've not understood what the answer meant. They've just Googled, they found a problem that's pretty much the same as the thing they're looking at, and they've gone, that works, pasted it in, and then everything's broken. And they've just assumed that it's not the thing that they've pasted. And they've put in debug, they've changed other stuff, and they've gone all the way around it without really understanding what they've pasted. Stack Overflow is fantastic. I wouldn't be without it. I can't even begin to tell you how hard it is to code up a PhD when you don't have these sorts of resources. But the problem is that the original poster will pose a problem specific to them. It will be answered specific to them. It may be locally efficient, but it won't be generically efficient, and it won't necessarily work for what you need. And at least understand it enough to change the variables to what something that makes sense for your code. And this makes me cringe all the time. So, maths. One of the reasons that I think that mathematics, at least a basic level, is important is that you need to think about what you're coding rather than just diving in and coding. Now, the very top line is the solution to the Towers of Hanoi problem for 3 pins. And as the number of disks in your problem increases, you end up with this algorithm that's double the number of previous moves plus 1. Now, if you ask someone to code that up, it's a really easy, obvious, recursive problem. It'll take them no time at all. And then you start saying, okay, I've got 5 disks, what's the answer? And they'll come back pretty quickly with the answer. Okay, I've got 100 disks, what's the answer? And depending on how the system's set up, they'll go, oh, max recursion level reached. I'll just change that. As soon as you start fiddling around with the inbuilt setups in Python, that should be a real red flag. But understanding when you get these sorts of recursive problems and how to solve them is actually a really good skill that not a lot of people have. The second line shows that simplified down to a single call rather than a recursive call. You get exactly the same answer. You put in your 100 disks, rather than an error, you'll get an answer almost straight away. So not only is it faster, but it gives you exactly the same results. The second set is something very similar and a bit more like what we deal with on a day-to-day basis. When we're looking at things in neural networks, we're looking at summations. And you can end up with things that look quite complicated, which on first inspection you go, I know how to code that, it's just a loop. And then you end up with maybe trying to simplify your loop, and you might end up with something like this that's pretty easy. It's just a loop within a loop, how hard can that be? But as your numbers get big, you have something hideously inefficient, something that will eat up all your memory, something that will take ages to run, but will look fine when you look at the code. And that's the problem. Without thinking about what you're doing, you'll have coded something that looks neat, looks beautiful and understandable, but you won't have got something efficient. And if you know your geometric series, you can simplify this into solving the inner loop and then the outer loop, and you end up with this answer, which again runs pretty much instantly, rather than doing a horrendous loop over 2 different values. If you can understand the maths behind what you're doing, rather than naively implementing what seems like a straightforward equation, you'll have code that runs so much faster. And as I put a note on the bottom there, a lot of people think that they can just call a library to do this for them. a lot of the libraries just run the loops. They don't optimize it. That doesn't count. So understand what you're doing. And you might have a third-party library that does all this optimization for you, but then that's another call, that's another overhead. If you can work this out up front, before you start coding, you'll have much more efficient systems. And by all means, put all this explanation in the comments, don't lose it, make it so that your code's readable for the next person to look at it, but at least then you'll have that one line that does something amazingly fast. One of the other things that I see really regularly, again, because people haven't been taught to code formally, is understanding the boundaries of Python. And I will stick to Python for this, because it's the language that most of the people I interact with use. But the same thing happens in other languages. Understanding your basic data structures, what's fast, what's slow, what grows as your data structure gets bigger. When does it start to become a problem? When does an O1 lookup, that's pretty static, become exponential? Simple things, strings. Most of the people that I deal with do string concatenation using the plus operator. It's really slow. It might not be slow on a single call, but if you're doing a lot of debug output, if you're writing to log files, if you're while you're training, you're doing all of this output to screen, which a lot of people do to see what's going on. It all adds up. Again, it's the pennies. If you understand how to do it in a Python way, it'll be so much faster, and it's still just as readable. The second thing is understanding all of the inbuilt features. If you know that map exists and you can use it, it's an order of magnitude faster than looping through the old way, because it's been pre-written and it's optimized in C rather than Python, which is more slow. So it's already been pre-compiled and it runs super fast. Regexes are another thing. You might think, okay, it's an inbuilt function, it'll run really fast, so it's fine to include it in my loop. But without understanding what search is doing, you'll end up with a much slower function. So for those of you that don't know, search, at this point, you're passing it in your regular expression and what you want that to work on. And what it's having to do is interpret that, compile it, and then run it. So you're getting 3 steps within your big loop. Whereas if you compile it beforehand, you're just getting 1. The larger your loops, and a lot of the things that we're working on in AI are very large, these really, really make a difference. So as I hinted at before, we can't all afford the latest and greatest. Much as I'd love to have a couple of DGX1s or the latest versions sitting around under my desk, we can't. I've worked a lot with startups, and you need to be really efficient in what you've got and sweat the assets, particularly with those early stage ideas when pretty much you've got $100 to spend on AWS and very little else. You need to understand how you can get the most out of your hardware, whether it's virtual or real. And if you are restricted by the demands of in-house, or even where you're going to deploy it, you really need to understand the efficiency of your systems. Otherwise, you will end up with either a model that can't run on what you need it to run, or something that runs ridiculously slowly. So up front, you need to decide whether you need a really big system that can solve the world, a horse-sized duck, or actually, can you do something much cheaper and much more creatively? Use the older cards. There's lots of them. They're really cheap. And do lots and lots of small models and then string them together somewhere else. The benchmark performance. I always see a lot of people saying, oh, I need this card. It's the latest and greatest. This works best for MNIST. This works best for something else. Or even if they're just using their own benchmarking websites, it works best for a particular game. It's not necessarily indicative of your networks, depending on how you've architected them and how you're interacting with the GPU. You might get better performance from a card that looks worse, or worse performance from a card that looks good. And you need to understand the value. It's easy to just throw money at a problem and get the biggest, the latest and greatest cards. But what actually is your best value per CUDA core, your best value per second of intelligence that you're solving? That's the key bit, and if you can hone that, you'll end up with faster, smaller, and more appropriate, cheaper solutions. One of the things that I've had to do a lot in the past, particularly when I've been constrained by hardware, is not only try and work out the tightest possible code I can, but also look at the other assets I've got on the machine. If I've got an 8-core CPU and a GPU, and I'm only using one of those CPU cores, I am wasting an awful lot. So you need to look at parallelizing the operations that you can, threading things. Your GPU should never be waiting for you to download data or manipulate it unless it needs GPU-specific operations. Have everything stacked up so you can batch it through quickly. TensorFlow's got some really interesting properties, one of which is, in order to avoid memory fragmentation and to make it run quickly, it steals all the memory of your GPU when you run it, by default. Which most of the time that's fine, because people generally only run one thing per GPU. But if you are training your models on lovely big GPU hardware, what that doesn't tell you is how much you actually need. Can you run it on a smaller card? Can you get away with something else, or do you really need one of those big top-of-the-range cards? But fortunately, they have chucked in this little option. This will make it slower to run initially as it expands out, but it will tell you exactly how much RAM you need on your card, which is really important. And you might find that 2 gig is all you need, which is very, very interesting. Alternatively, you can look at your networks and calculate it yourself with all the tensors and variables, but who's got time for that? That's one of the reasons why we're in this place in the first time, is because we want speed of development over efficiency. The unnecessary imports, again, something that I think should be really basic, and I think also comes from people not understanding the code they're using and cutting and pasting, is quite often I see people deliver me code that's got every single possible data science library in the world imported at the beginning. And not the specific bits they need, but the full libraries. NumPy on its own is 320 megabyte. Even if you don't use it, if you import it, that's just sitting there in your memory. Now, to get around this, sometimes people put imports within functions they don't call very often, which may or may not work. When you import in Python, the first thing the machine does is check to see if you've already imported that library. That is an overhead. If you are importing in a function that you call regularly, the first time you call it, it will import the library and it'll stay in memory. But every other time you're adding an inefficient call that you don't need. So think about where things need to be. And do you really need every single data science library? Can you use the similar function from another one? But that said, it's always better to use the best tool for the job. Now, when I release these slides, I've got the data behind this and the code examples, but this is a blog post where a basic linear regression problem was coded in pure Python using NumPy and using TensorFlow. And okay, the code is slightly different because they're making use of different setups, but to solve the problem and get to the same correct answer, pure Python is, gosh, about 75–80% slower than using NumPy. Pure Python is quite rubbish at numerical manipulation. So be careful what you use and use the correct tool. But that said, you don't need all of them at once. It's just bloating your system. So I can assure you that this is completely static, even if it looks like it's moving. And if you don't believe me, I have a printout later. So going back to us, we actually throw away 90% of the sensory inputs we get, particularly from our eyes. One of the reasons visual illusions like this work is that your eyeballs are constantly moving because they're only taking in 10% of the data. And your brain is making the rest up. It's one of the brilliant things about our brains. This is why we're fooled by visual illusions. This is why we're fooled by audio illusions. This is why we see things in the corner of our eyes that aren't there. But we are very, very good at inferring from minimal amounts of data. If you are throwing too much data into any AI system, you'll end up with problems. You might need more data to learn what you need to learn from it. I mean, particularly in visual recognition. If you're throwing in super large sort of raw iPhone images in, and you're looking for something that's tiny on the screen, it's going to take a lot more data to learn the important features than if you're just cropping down onto the important stuff. And it's the same for time series data, it's the same for everything else. If you pass too much in, you will end up with an over-large network. Take some inspiration from human biology. Don't look at the noise, focus on something and learn that. This is where the data science part of AI comes in. Understand your data primarily. If you understand your data and what is important in the data, you'll end up with better results with a smaller training set. The other thing that pains me is not every problem needs TensorFlow. Not everything is a deep learning problem. Depending on how you define AI, the key thing is the output that appears intelligent. That does not need to be a human brain-inspired network. It could be as simple as an if this then that approach, as long as that encapsulates the problem and gives you the right answers. If you use the overhead of a huge deep learning network when you don't need to, you are wasting time and resources. And if you want to understand quite how ridiculous this is, there is a wonderful blog post, which is in the notes for this slide, about a guy who was asked to do the FizzBuzz coding test, and he did a deep learning version of it, which is absolutely ridiculous, and far more time consuming and more code than you'd need to just do the standard solution. So this comes back to understanding the problem. To understand the problem, understand your data, do the data science, and then pick the best tool for the job, and then you'll end up with something much better. So this is a technique that's become trendy in the past few years, or actually first came out in the late 80s, I believe. So unless you've got the sort of brain that can think in hyperparameter space, most people start with something that they've learned before, start with a pre-trained network, and they might tweak it a bit, but generally they'll tweak other things than the hyperparameters. However, using optimization, it's a Gaussian-based process. You can search your parameter space pretty efficiently. Okay, the actual thing is fairly inefficient, but the fact that it's learning from its previous steps, unlike other optimization methods, means that you can very quickly get to your optimal goal. And there's a couple of papers, one from just 3.5 years ago, one from a couple of years ago, and this wonderful open source library, Gaussian Python optimization, which is still maintained by Sheffield Machine Learning, which is actually rather useful. And that will help you optimize all of your hyperparameters, and it's well worth looking into. Something else that's become trendy recently, although also stems from the late 80s, early 90s, is pruning. So you change your network, and it's a huge behemoth, and you want to make it smaller. So you work out what are the nodes in each level that aren't relevant? What can you take out? And it's quite a complex problem, because every time you change one of the levels of your network, you're then changing the inputs into the next level of your network, and so on and so forth. So it can end up quite a complex, time-consuming problem. Now the question is, does it work? And the answer is yes. There's a wonderful paper from about a year ago showing that you can make some assumptions. You can simplify away items that aren't relevant, and you can get a 5 times speed increase on your network with only a minor error increase, which may or may not be acceptable depending on your problem. Which is great. However, it's possibly something that most people in business don't care about. It's too time-consuming. And interestingly, last week, there's a paper from Crowley et al., which I was reading on the train in this morning, basically saying that we shouldn't bother. And they've done some interesting tests where they've taken networks that are big, they've then pruned and tuned them, and then compared them against networks that were small to start with. And they discovered that a well-architected small network outperformed a pruned network on all the data sets that they passed through it. What was interesting, though, was that they then went on to say that if they took a pruned network and trained it from scratch on a new problem, that then outperformed a small network. So there is some value in the pruned networks, as long as you don't waste the time and energy doing it yourself. And at the end of the paper, they propose that we're pretty much on the verge of, rather than taking our current set of networks that we all know and love and download and just throw our data at them, we might be on the verge of getting a whole set of new, hyper-tuned, hyper-efficient networks to work on. So it's something worth thinking about. Particularly academia are very, very good at doing the state-of-the-art, fastest, most accurate. So let them do all the hard work, and then those of us in business can take them and apply all the other efficiencies around it. One of the other things that has become trendy recently is quantization. You've got an awful lot of variables in your models, an awful lot of variables, and they're all really, really high precision. How many decimal points of precision do you really, really need in your variables? It depends on your problem. Tensorflow, bless it, has some wonderful built-in functions that will do this for you, that will immediately kill the accuracy of all of your floats down to 8 bits, which may or may not work. For their systems, they've said it has a major impact on accuracy, but again, it's going to be very, very dependent on the problem that you're putting through it. I'd say that this is probably the lowest on the list of things to do. When guys in my team come to me with their new models, I have a bet with them as to how much I can improve it by. And quite often they won't take me up on the bet. I usually say that I can improve the speed of what they're doing with no drop in accuracy by 5 times. And they don't take me up on this because they're very nervous about all the things that they've done. And it's mostly those top few things that they haven't done. By far, the biggest performance increases you'll get is coding properly, understanding your libraries, and just being mindful of your resources and not doing things in a strange manner. And you can find all these things using the profiling tools that come with Python. They're out there, they're very well documented. Start with those, you will get huge performance gains. And then you go on to the extra things. So look at things that people have already optimized. Depending on your problem, you might be able to get something off the shelf that is already purported to be 10 times faster than the current state of the art. They are great. Let the academics, let the universities do all that hard optimization for you, and then just take what you need and do your data science on top of it. And then the bits towards the end about parameter optimization, pruning, and quantization, they're great. On the whole, they're not necessary. You can get the majority of your speed up just from good coding practices, absolutely. If you want to go further, then ditch your libraries altogether. Ditch TensorFlow, ditch Python, code in C directly into CUDA. However, you're going to be spending a long time doing things that way. If your problem calls for it, however, you'll get something really, really good. Some of the AI security companies, the standard libraries don't work for them just because of what they're looking at and how they're doing. And one in particular has stated that they spent a year, although they didn't say how big their team was, and they wrote their own framework in C directly into CUDA. And it's hard to do a like-for-like comparison, but it was over 70 times faster on similar problems than doing the same problem in TensorFlow. So if speed and efficiency are really, really important to you, depending on what you're doing, go straight to that level. If speed of development is important to you, use the frameworks and code properly. That's the way to go. Thank you.